interaction with its environment. While before the first data release, and especially the second Gaia data release, we had a more static view of the galaxy in which we live. So today, this is maybe like this. It's not moving. No, I am maybe. Okay, here. So today I will present you, first of all, Gaia, and especially the last data release of the Gaia satellite, but also the work that we have been doing in Nice. And many of the works I will present you in the following have been done in collaboration with Patrick de Lavernie, and also the four young people that you see here: Pedro Alonso Palicio, who's a CNES workshop postdoc, Eloisa Poggio, who's a Marie Curie fellow, Emanuele Spittoni, another senior postdoc, and Gabriele Contursi, who's in the last year of his PhD thesis. So this is the outline of my talk. First of all, I will introduce the Gaia revolution. And while I will not spend much time explaining all the different kinds of Gaia data, because many of you already know it, we are already at the third data release after this early year 3. I will insist more in the keys of the success of the Gaia project and why I think this is really important for us and how it will be evolving positively in the future. Then I will discuss the chemical cartography of the Milky Way, of which I'm responsible within the Gaia DEPA consortium, and then the different results and galactic evolution of the disk and also the halo, and I will finish with my conclusions. So first of all, Gaia, the Gaia revolution and its keys. I have to put things in context. I have made this small animation with the concepts of the universe through the time. It's of course just some of them. I could have added many more. So the evolution of our vision of the our cosmos, our galactic environment through the time, and you see that even recently in the 20th century, a lot of improvements, observational improvements arrived before Gaia. So this is the Gaia, what I'm going to show you here is the Gaia DR3 data, which has added to previous data releases the physical dimension of the objects that the Gaia is observing, with the chemo-physical parameterization of many of them. And the movie that you're seeing here has been produced by the Gaia Consortium to illustrate the chemical cartography of the Milky Way. So this is going through Zoom, so maybe it's a bit truncated in the vision, but yeah, the colors of the stars here are telling you the chemical composition, with redder stars being metal rich and bluer stars being metal poor. So Gaia DR3 has allowed us to see a Milky Way in which we can dive in. Is something that looks like a simulation, but it's not. In this animation, the positions on the metallicity of the star are real observations, and we see the stars moving, and we have this Milky Way that finally allow us to see galactic landscapes that help us to illustrate all the things that were, all the characteristics of our galaxy, the structure, the chemical gradients, and all these things that we were teaching and reading in the textbooks can now be illustrated thanks to the Gaia data. So very briefly, the main objective of Gaia was to determine the positions, the motions in 3D of almost 1% of the stars in our galaxy. And what you see here is the Gaia focal plane, in which, you see my pointer? Yeah. So the light of a star passes first on the astrometric CCDs, which bring us all the positions of the stars and the parallaxes, then goes through the BPRP spectrophotometers, which are helpful, for instance, for determining not only the colors and the magnitude, but also the temperature of the stars. And finally, through the Radial Velocity Spectrograph CCD, which is a medium resolution spectrograph that is allowing us to provide the temperature, the gravity, the metallicity, and all the different individual chemical aromas that I will show you later. So what are the keys of for not mentioning him? Okay, so the Gaia, the first key of the Gaia revolution are, of course, the Gaia parallaxes, which are providing us with the depth of the sky that we were lacking before. We had this very high uncertain distances to the stars, and now, thanks to Gaia parallaxes, we have this direct estimate distance measure with an incredible precision. So what I'm showing you here is the evolution of the catalogs of parallaxes through time. The first catalog had 3 stars and was back in the 19th century. When this happened, the president of the British Royal Astronomical Society said that we had lived to see the day when the sounding line of the universe of stars had at last touched bottom. So finally, we're able, if estimating the distances, the stars stay at large but finite distances. Gaia is pushing this adventure to an incredible amount of stars, bringing us a 3D picture of our galaxy and beyond. The second key property of the Gaia satellite is, on the Gaia project, is number statistics. So as I said before, Gaia is surveying about 1% of the stars of our galaxy, and this is extremely powerful to explore not only the median characteristics, chemo-physical characteristics of the stellar populations, as we are doing more or less when less large catalogs are used, but we are also able of exploring the queue of the distributions. We are really inside the galaxy with a realistic exploration of all the different kinds of objects. So we have about 1.5 billion stars with astrometry and photometry. In Gaia DA3, we have 33 million stars with spectroscopy and radial velocities. And as you will see later, we also have almost 6 million stars with chemo-physical parameters. So this is what you see here for the photometry. And Gaia DA3 has published these beautiful color magnitude diagrams in different photometric systems. And this is illustrated in this paper here by the Gaia collaboration and Montegrifo et al. And we have, therefore, we are able to identify on the different evolutionary stages in these extremely beautiful HR diagrams using, of course, the Gaia distances. And this is an illustration of this Gaia DA3 catalog of radial velocities, where we see the disk rotation with the stars coming towards us and and rotating in the disk, but also all the different objects like the Large Magellanic Cloud, the SMC, different objects and other satellites, and even the Sagittarius dwarf galaxy here behind the bulge. And as I said before, we also have this all-sky chemical cartography of the Milky Way that I will come back later to this, thanks to 5.6 million stars with chemo-physical parameters. The third important key of success is the stability and the precision of the Gaia observations. These space observations do not have to care about the Earth atmosphere, and thanks to the continuous observations for years, the control of systematics is extremely good, bringing us spectra as the ones that you see here. This is the RVS wavelength domain, and thanks to this, we have been able of estimating the abundances of heavy elements like cerium, as you see in this plot, from very tiny lines, because each photon means something here. And this high precision is also helping us to produce diagrams like this one, HR diagram. This is the gravity versus the temperature. And as you can see, we can identify the bump, the clump, the young stars in the blue loop, RGB and the AGB separately, which means that we are able of having an extremely high precision in temperature, for instance. And the final Gaia treasure is time series. That's these continuous observations for months and months and months that are providing us, allowing us to see the evolution of the system. So this is illustrated, of course, by the proper motions that were published already in the early DR3 release. But other nice illustrations of this time series of this evolution is the solar system acceleration that was also estimated in the early ER3 from the aberration of the quasars' positions. So we see our solar system accelerating towards the galactic center. And the third point is the stellar variability. Here, this one. Here is is the position of the quasars, which are supposed not to move. Okay, and we see them moving because of an aberration effect, because in fact the solar system, our position is accelerating. And yes, and the other illustration is the capability of Gaia of studying stellar variability. So this is the variable HI diagram published by Ayer et al. In this year in the Gaia D3, where you see different types of variable stars, classical Cepheids, large period variables. You have all these, you can find in the paper the different definitions here, and here you see the time. I find this amazing number of days. So Gaia is observing all the time, still observing now continuously, every day, every day, every day. Okay. And this is why we are really seeing the galaxy evolving for years. Okay, so what does this mean for the spectroscopic data? So I'm now going to show you the results that we have been able to produce for Gaia D3 thanks to the data of the Radial Velocity Spectrograph that is centered in this infrared calcium triplet wavelength domain at a resolution of 11,500. To analyze this spectroscopic data of millions of stars, we had to implement a pipeline and develop from scratch, because even if the paper that you see here is our paper of DO3. The first, the algorithm that we are using here has been published in 2006. It's part of this ESA fellowship that I got for coming to France. So this is 18 years of development for arriving to the to year 3 last June. So our module that is called GSP-Spec, Generalized Stellar Parameterizer, is producing the atmospheric parameters of the stars, the individual chemical abundances, a differential CN equivalent width, and the parameters of a diffuse interstellar band. During the operations for the DO3 that take place at the CNES in Toulouse, we have treated almost 7 million spectra. We have performed Monte Carlo realizations of its spectrum to get the uncertainties in the different parameters that we were producing. And the algorithm is, of course, very fast. It takes about 1 second to treat one spectrum to produce all these different parameters that you see here. This was mandatory for Gaia, of course. Well, this is the Matisse algorithm. Maybe at the end, if you have some questions, I can answer to them. It's a projection method where we project the observed spectrum into a basis that is determined during a training phase. So this is why then the application is very fast. And then the individual abundances are estimated thanks to a Gauss-Newton method. It is an optimization method around the individual lines of each element to estimate the individual abundances after the parameters are determined. So this is the GSP-Spec at work movie where you see different high synapse noise spectra in RVS spectra. So on the top, you can see the results for the effective temperature, the gravity, the global metallicity, and the alpha over phi abundances. And on the left, you see the individual abundances of the different elements that are derived after deriving the individual abundances per line, which are later on combined. As you see, we are producing up to 12 different chemical elements. Of course, it depends on the type of star. Some elements are not detectable for some stars. Depends also on the signal to noise. And it's interesting to point out that thanks to the RVS data, we are having diagnostics of different nucleosynthetic channels from exploding massive stars, type 1H supernova, neutron star mergers, and dying low mass stars. So this was somehow unexpected for a spectrograph of the short wavelength domain and resolution of Gaia, but thanks to the quality of this space data, it has been possible to do. It is being possible because we are still working there. This is the distribution in magnitude of the stars for which we have published the atmospheric parameters and have been treated, and that you can find in the Gaia archive there. So you see also for comparison, the other spectroscopic surveys from the ground is Apogee, Gala, and the Gaia ISO survey. You see that mostly the ground-based surveys are, of course, the number statistics is much smaller, but they are also complementing the Gaia observations in the fainter end, magnitude end. These are the numbers of the different individual abundances that have been derived. The different blue colors that you see here correspond to different quality flags because you have, of course, different qualities in what has been produced. So the Gaia RVS GSP-Spec parameterization is model-driven based on for DO3 in a Mark's model atmospheres and turbo spectrum. We have spent a lot of time selecting the lines that are there for the individual abundances. And if you use this data, I have a main message here. Please use the quality flags. because yeah, it seems stupid, but many people can think that you simply click and download the data. As for the parallaxes and there was, or the astrometry, it was quite simple to use. Here is like for other surveys, say apogee, for which you have to look and take care of the quality flags. So please use the quality flags and read this paper, because it will help you a lot with different tables that I have pointed here, and also with the calibrations. So the data are not calibrated in the archive, so people can also find their own preferred calibrations, but we are proposing some polynomial calibrations that are easy to use. So I go back to this old sky chemical cartography that I've mentioned before. Now you can see the same cartography, cut it in slices of distance, and you see in the in the closer bins, of course, the disk, the metal-rich disk in which we are embedded. You see the color again gives you the global metallicity. So we are embedded in this metal-rich disk, and then as when we are moving farther away, we start to see the slightly more metal poor thick disk, and then finally the halo, and even in the more distant bin we see also the Magellanic Clouds. Okay, here these are the different bins. You see the Magellanic Clouds here. I was really amazed when I realized that we got them in the box already for this first data release. That was for us the first time that we were publishing data, and it's just 34 months of observation. So you can think that with time the signal's noise will increase. This is the same cartography but with the alpha over phi, and again, so you will identify the disk in the closer bins with the where the alpha over phi ratio is lower, and then you have the thick disk with a higher alpha over phi and the Magellanic Clouds in the back. So the galactic disk now, some results. After that was the catalog, and now what can we do with this catalog? So one important thing to keep in mind is the selection function in this extremely large catalog. It depends on what kind of stars you select. You will see different things. You will be found in different parts of the galaxy. So you see here this what we have called massive in this performance verification paper. So these young stars, blue loop stars, Cepheids, etc., that are tracing the spiral arms, as you see on my illustration on the top. And then if you take the RGB above the clump, which is the part that is less biased, you will find this sounding of the disk much more homogeneously. So if you select the young stars, as I said before, you can trace the young thin disk and see the gradient, the chemical gradient that we already know before. But here we can trace it and quantify it very precisely at different distances from the galactic center with field stars and with open clusters. I will show you before. And we can see also the flare of the disk. So you see here how it gets thicker. Looks like get thicker when we move outwards. And if we add the radial velocities and the astrometry, you can see really the disk moving, rotating, and with us inside. If we use the other tracers, the luminous RGB stars, then we can observe the vertical gradient of the disk moving from the thin disk to the thick disk, and also the radial one. We have quantified the symmetry above and below the plane, and it was strikingly important. We can then use the alpha over phi estimates versus the metallicity trend to check for to study the thin and the thick disk populations. And in this view, you see a color code with the galactic rotation, the V5, in beams of Z and R, so distance to the plane and distance to the galactic center. We have enough stars to do these crazy maps. We have spent a lot of time to think how to illustrate the catalog. And in particular, this figure shows you that we can find fast rotating stars well above the disk in the external parts with chemical abundances typical of the thin disk. So these are really showing us this extremely important flare of the disk. So now a word about the alpha over phi of the RVS. So you see on the left two plots of the calcium over phi, so determined from the calcium lines for the RGB population and for the young massive stars. And on the right, you have more or less the same thing, but for a subsample of high synopsis noise data, plotting the alpha over phi. And you see that the trends are very similar, and the separation of the thin and the thick disk disappears quite early at around -0.4. Okay, depends. They are merging here. This is normal because, in fact, what we are estimating, the calcium lines are dominating all the alpha diagnostics for the RVS, and therefore this alpha is the calcium abundance. And what I'm showing you here is the very good correlation of the alpha over phi from Gaia with the apogee calcium, for which we have in this testing sample. Once we have calibrated the data, a very small spread. Okay. So these young populations appear to be depleted in metallicity and alpha over phi, but also other individual elements. We have pointed out in our paper of year 3, because we have been checking if there was a mistake in the analysis. We haven't found any mistake, and on top of that, when we cross-match it with ground-based spectroscopic surveys, we realized that we were on the same scale. It's just that other surveys had less stars. And with Gaia, we had several tens of thousands of stars, and this was strikingly there. We had these young stars here, down here. Okay, but you see that our cross-match with apogee shows that we are in the same scale, and these stars are also depleted in apogee. Whether this is real or it is an artifact, we are all having the same result. I will go back to, so yeah, we have been working a bit on this. Certainly different explanations can be given. One of this is the one that is proposed in this paper by Emanuele Spittoni, in which using his models that think the Milky Way as the Milky Way history is modeled by a sequence of different accretion episodes. He has added a new recent info that would be also in agreement with the recent self-formation history reconstruction for the Milky Way. And this will loop here at the bottom, explaining the observations. We have also used the same chemical evolution approach, and this time with an analytical solution model that includes type 1a supernova that we are up to, we hope to publish very soon. And this is what you see here. In this time, we are adding an extra time with the delay time distribution for taking into account this type 1a supernova. And so this analytical solution is very fast and can be used in many different ways. And because I'm here and because I'm collaborating with Sebastian Perani, who's now at OCA, but was here before, and is part of the collaboration with Johan, who was there before. We have been applying this analytical solution to a simulated galaxy and trying to reproduce again the star formation history, and then to produce the chemistry of this galaxy. So Gaia is also not only providing the alpha over Phi estimate, but also the individual abundance estimates, as you can see here. And we have been spreading the abundances that we
plus d'un mois pour avoir la décision
to
délibérée, ils appellent ça.
It's hard. So yeah, so we were also the spread that we saw. I don't know if this is working. The spread that we see is real spread, is not uncertainties, and we have checked this with the kinematics and the orbital properties, and this is what you see here for the color code with the V5 or the orbital eccentricity. So you see the thin and the thick disk properties that correspond to what it should be. As I said before, we are also producing heavy element abundances like cerium, neodymium, and in this paper of Gabriele Contursi, we have studied the radial gradients in cerium over Phi in the galaxy, radial and vertical gradients, and then also comparing the cerium over calcium versus calcium over H, as you see here. We have been verifying that indeed HB stars seem to be the main responsibles for cerium abundances in the disk. As I said before, Gaia is observing also stars in open clusters, and for D3 we had 687 open clusters with Gaia chemical in the Gaia D3 chemical database, and for which we have estimated the here, as you can see, the radial gradients for the metallicity and the alpha over Phi with a color code of the H, because these are open clusters, so we have ages for the objects, and then this allows us to study also the slope of the gradient, the evolution of the slope of the gradient with H. And I was extremely happy to see that just a few days after the data release, Nikos Prantzos produced a fit with, thanks to his models of this data. This is what you see here, of both the gradients with radius, but also the trend of the evolution of the radius, so of these trends with time, and with an amazing good fit. And well, here's thank you, Nikos, for allowing me to share these plots from a paper that he's preparing. These different model approaches are extremely important because of the different competing mechanisms of the galactic evolution, and we really need all these different views, model views, to understand what we see. One of the main results of the Gaia D3 is that the chemistry is always a marker of the different disk perturbations that appear either in the form of phase spiral perturbations or substructure in the kinematic space. We have, for the first time, detected the correlation of in the thin disk phase spiral that was found before by Teresa Antoja et al. We have detected for the first time the correlation with metallicity. So you see here again appearing as color code with the metallicity, especially in the external parts of the disk that are less bounded. You see that the more meta-rich stars are those are the stars that follow better this space perturbation that is caused either by the disk crossing satellite like Sagittarius, dwarf galaxy, or by other more internal mechanisms like the Barclay. We have also explored the outer disk populations and finding again that there was a chemical bimodality attached to the kinematical bimodality that was seen in this substructure in the VZ versus V5 plots that were seen before in the kinematical space, but for which no chemical diagnostics were at our disposal. And regarding the famous ridges of this chemo in the kinematical space that appear already before with other Gaia data, previous data releases, we are again seeing that these azimuthal dependencies in the metallicity correlate. This substructure correlates very well again with the metallicity, with a metallicity excess tracing the substruction. And for the first time, we were able to estimate in the orbits. We have now the orbits of 33 million stars of our galaxy. And we have used in particular the orbital actions to study the chemo-dynamical correlations of the stars in the disk. And in particular, the radial action JR, which is characterizing the radial amplitude of the orbit, so sort of proxy of the eccentricity, and the angular momentum. And for the first time, we have identified substructure in this orbital space that is once again attached to a metallicity excess of the populations in this substructure. So we see this very in-depth link between the chemistry and all the motions of the stars in our galaxy. And it's important to keep in mind that chemistry is conserved through time mostly, with some exceptions, but it's mostly conserved with time while the orbits are not. Now the spiral arms, thanks to the high precision of the HR diagram that I was showing you before, and to the high number of statistics, we are able of selecting stars in different age spins, as you can see in this figure here. And we have defined a different sample A, B, and C, and then you can see here the view distribution in the galactic disk. You see that the younger stars trace the spiral arms, and then more or less this is smoothing for older populations, but we see that there is a metallicity excess that is associated to the spiral pattern that was traced by the young population. So a very clear metallicity excess. And more recently, studying again the radial action, we have in particular exploring this old population in the disk, like cutting here only giant stars. We have discovered this pattern in the JR action that is following the spiral pattern, right? So as you can see here, this is color-coded with JR, and the redder regions are those of with the stars in more circular orbits. And when you overlap that pattern that is here in gray, in a gray scale, you overlap that with the pattern of the different patterns in the literature of the spiral arms, you see a very good correlation, not one-to-one, not perfect one, but a very good correlation. And we also find the spiral arms in the overdensity of the older stars. So the spiral arms are also somehow influencing not only the orbits, but also, of course, the distribution, the density distribution of the older stars, despite the fact that they are moving around the galaxy. So I arrive now to the halo. The Gaia DA3 content has, of course, many stars in the outer parts of the galaxy. And you can see here the energy versus angular momentum plot on the left for the halo stars with radial velocities. We have cut it, the disk stars here. Otherwise, the contrast wouldn't be so nice. So this is a density plot. And on the right, you can see the overdensity plot in which we can detect the different substructures in the halo coming from the past accretion events, with the famous Gaia Enceladus event here, overdensity here, but also others like Sequoia, etc. And we have, once we have identified that, we can go to the chemo-physical catalog that has less stars, but has a subsample of those stars, and to find, for instance, stars in Gaia Enceladus, Sequoia, Helmi streams, etc. Here is part of the film I showed you at the beginning, where the Gaia Enceladus stars looking blue because they are, of course, metal poor. And the Gaia chemical diagnostics allow also to detect these accreted substructure in the chemical space, in the alpha over Phi, because we can, well, there's some contaminants from puffed up disk and some halo, in situ halo, but we can see the low alpha over Phi pattern of this, typical of this accreted accreted stars. And we have even some cerium abundances in few stars in different accreted substructures, as explained in this paper of Gabriele Contursi, where, well, the number of statistics here is really small, but, well, we are trying to compare this cerium abundance in different accreted systems. There are also extremely metal poor stars in the catalog, as illustrated here in this figure. You really need to use the quality flags and to check the paper, because we are providing with a recipe to clean for contaminants from hot stars. But they are there. So I arrived to my conclusions. So the Gaia future is bright, because Gaia D3 is just a quarter of the total data that Gaia will produce, just 34 months out of 10 years at the end of the mission, of the extended mission. The end of the coal gas and the operational phase will happen between January and March 2025. But of course, we are stocking the data and storing the data and preparing our pipelines for analyzing more and more and more data. For the RVS, this extension of the observations is extremely important, because we are getting more and more higher and higher signal to noise for the stacked spectra, and enlarging, of course, the volume that is sounded by the catalog. We will move from 5.6 million stars parameterized this year to about 30 million stars in the next DR3, and probably around 100 million stars at the end of the mission in 2030. Of course, you have to think that this is complemented in the faint part by the new high-resolution spectroscopic surveys like WEAVE and FOMOS that will produce in the meanwhile between 5 and 10 million stars in the faint magnitude domain. The time series in the next Gaia Data Release, we will also publish time series chemo-physical parameters for Cepheids and RL Lyra. This will help us to refine the pure luminosity metallicity relations and to use these standard candles to increase the precision of the Gaia distance towards the bulbs, the outer disk, the halo, and the surrounding satellites. So making Gaia climb the distance ladder. And in Gaia 2030, Gaia will have recorded 10 years of our Milky Way's history with all the impact on our vision of the Milky Way that this will have, of course. So it is extremely important to keep the synergy between the models and simulations and the observations, even including the cosmological context, to be able to disentangle all the different processes at work that are producing what we see in this chemo-physical space. And so I thank you for your attention. I leave you again with this movie that we have produced. Thank you for your attention. Thank you.
Thank you very much, Alejandra, for this extremely interesting and very well made talk. Thank you very much. I'm sure there will be many questions. Gary, to start.
Thank you, Alejandra. You know, you have the fortune of working in 10+ dimensional space, which is at the same time wonderful and very difficult.
Yes.
And you produced fantastic results. And when you hear a talk on Gaia DR3, we know it's going to be very full of information. So it's hard to digest it all. So I was intrigued about the point of you finding young stars of low metallicity. And you mentioned they could be gas and fall, recent gas and fall. But could you locate where these stars in particular locations, or did they have particular kinematics?
Yes. So they, yes. So they are located in the spiral arms. This is why, to be honest, I was playing with the data before the Gaia Data Release when we were working on this. And when I selected naively this part, what I've called here massive, and then I said, wow, we see the spiral arms. So obviously these are young stars, and it's happily they are there where young stars have to be. So there's no doubt about this. Some of them are blue loops, some others are cepheids, and so they really trace the spiral arms. They're in the spiral arms. Kinematically, they are cool. So unfortunately, I don't have here the plot, but if you do the distribution of V5, VZ, etc., VR, you have a very narrow distribution compared to the RGB counterpart, the older stars. Then, yeah,
Is that metallicity?
This metallicity, the same, yeah, on the right too. So you see the, you see the gradient, the radial gradient, some azimuthal variations linked to the spiral arms, by the way. I agree with you that it's puzzling, and this is where they are, okay? It's puzzling, and of course, my first reaction was what have been done. What's the mistake that we have done, right? And we have discussed a lot, and I have checked. Well, I don't have it here, and in one paper we are showing the fit of a specific spectrum for one of these stars. The fit is wonderful, and then when we cross match with other catalogs, and again, well, our parameters and our abundances were on the same scale. You see, well, this is what we get, right? And this is why I decided to publish like this and say, honestly, they appear depleted. Okay. One possibility is that as we are working in 1D LTE analysis, maybe if we push this into some direction, it will change. We are now taking care of this with some colleagues at OCA to check for non-LTE or 3D trends if they can explain it, but why not? but otherwise we have to find another explanation, right? So the one that we have published here with Emanuele is one possible one. Probably Nikos has another one, and I'm really interested in knowing his opinion. This is the vision of one person working on chemical evolution, and as I said here, modeling the galaxy as a sequence of accretion episodes. And it's true that looking at the star formation history, you have looks like there's a recent star formation episode, probably maybe linked to the Sagittarius crossing of the disk. Well, this is one possibility. I'm not saying that is the only one, okay? But this is indeed one intriguing result.
No, I have no explanation, but this raises a very interesting point. Actually, Gary, this was the question I would like to ask to Alejandra. There is an important point, because for the last 15 years or so, we have seen that the metallicity of young stars and gas in the solar neighborhood is solar, more or less. And also the alpha over iron. We know that through the gas and also through the young stars, the B stars. It's the papers by Nieva and Pribila. And so this would mean, this is more or less the standard picture for the last few years. We think that since the sun was formed 4 billion years ago, until today, there has been practically no chemical evolution locally. Or at some point, the metallicity was continuously diluted. Because in principle, in standard models, metallicity increases with time. It's hard to avoid that. You have star formation, or galaxy is still active. So at best, you can hope to have the same level, to keep the same level. And this is what we were seeing with the B stars, both in Orion and B stars in the field. Now your results are really surprising. You know that. I mean,
yes.
Low metallicity and lower alpha. And I don't know how to do that. I mean, if we evoke a star formation episode like these ones, the star formation increases basically metallicity.
Yes,
okay,
you have to fine tune.
It's something we have to check, but the non-LTE thing is also good to follow.
Sure, sure. We have not saying that this is our last work. And yeah, I see Katya raising her hand.
Just want to make a comment that you mentioned that in apogee, you find that we see the same, and then the systematics is completely different.
Yes.
Right? In apogee, we're looking at lines in the infrared, it's completely different. So if we see in apogee and we see in the optical, I think from the point of view of the observations, it's pretty strong that it's real, I think.
Okay, so it depends on which observer we talk to. Because the B stars guys say that it's solar.
I mean, hotter stars. These are, yeah, it's true that this is a new way of tracing the young population. And so it's true that I think it's because of the number statistics, because they are not very, there are many more. They are rare objects because they're massive, so the time that's spent at that moment is short, so you really need a very large catalog. So apogee has also these stars, but they are maybe less striking. Here you cannot miss them. You see, what's that? But well, I agree that we have to not to neglect any possibility.
Completely different. At the beginning, you mentioned an acceleration of our solar system. What does it mean more precisely?
What does it mean? So it means that we are, well, the solar, our sun is in a potential, okay? And of course, you need a very extremely high precision astrometry to see the velocity of the stars varying with time. So this acceleration in the galactic potential. To see it on other stars, you need a precision, I think it's of nano arc second, so something that even Gaia does not have. And normally with the new generation of very high resolution spectrograph, you could see that in with time in the radial velocities. But for the moment, Gaia is able to see in it as this aberration effect of the quasars that are very far away. And so it's our own precision that is accelerating, and this is what we see. Well, I put it as an illustration of the fact that Gaia is producing time series data, okay? But it's not my field
Well, it's quite
research.
normal here if you think, because as Alejandra said, we are in a potential. The sun doesn't just go around in the galaxy. It is making epicyclic motions. It's going up and down the plane. So there is acceleration at some point, but it's very hard to see. That's what they did. So it's amazing, really.
It's amazing. And if one day we are able of estimating this acceleration for more stars, I think that the most promising path is that of the high resolution spectrographs in the next 10 years or so. Then we could constrain this galactic potential in a very direct way. And this is important because there are a number of uncertainties related precisely to the definition of the galactic potential.
Thanks for this talk. I mean, I'm quite flabbergasted by the amount of data that you showed and all the results. And when you outline the next coming years of Gaia and the large amount of data that you're going to have in the future, my question is, I mean, from all you've learned now, what are you expecting from these increase of data? And
yes, so I have been looking at what is going to come for defining the priorities of our group, and there are several things. The first one is in the next data release, we will have much more stars in the halo with estimates of the metallicity and the alpha over Phi. So this halo substructure will be much better sampled than now, because the signal to noise is increasing. The number of stars will be much larger. We will have also more stars in the satellites. And as this is an extremely homogeneous data set, this somehow compensates also sometimes for the lower resolution. And so you have all these 30 million stars in the same frame, and you can compare in them. It's very informative. The other thing I mentioned is this time series parameters for the standard candles. This was not planned before because our module was intended to analyze only stacked spectrum. But I say, well, we are saying that these are Cepheids, and then we produce one set of, well, just one set of parameters on the stacked spectrum. While this thing is changing for maybe 1000 Kelvin of temperature. So we will produce these time series parameters, and I've been checking, and there will be something like 3,000 Cepheids in the next catalog with chemical parameters. We will be able, if in a large metallicity domain, both in the Milky Way and the Magellanic Clouds. And indeed, we will be able to improve this pure luminosity metallicity relation that has still an important uncertainty on the metallicity dependence as never before, because and I think this will be a big step for the next Gaia Data Release.
Solve the problem of H naught. Yeah, because now there is a problem. I mean, what is the Hubble constant? It's based on this.
Exactly, and indeed, I've been checking this for H0 and checking a few of the last papers of Rees and et al. And the metallicity uncertainty takes into account around 1/4, 1/3 of the total error budget of H0, because they are using compilations of metallists from different publications. So they are really losing precision there. And I think that we can indeed make Gaia climb the distance ladder like this.
Yeah, I have a small technical question about the RVS spectra. The calcium, infrared calcium triplet is in principle a luminosity indicator, but at some point you mentioned also calcium abundance. So how do you separate the two effects? Are you using external data in addition? Or?
No, so we, as you say, this calcium triplet is also carrying a lot of information on the gravity, so this luminosity, the temperature, and then of course the metallicity, the abundance, calcium abundance. So our algorithm is trained on a 4-dimensional grid that is capable of disentangling this different degenerate effect on the flux of the calcium lines. Of course, some degeneracies remain, and we could maybe help it, especially for dwarf stars, to constrain a little bit better the gravity with the parallaxes. At present, we are not doing this. It works quite well, as I've shown you before. And we are producing purely spectroscopic parameters without BPRP or without other constraints, which on one hand is this independent check is also useful for understanding different methodological uncertainties, but this is what is done at present.
Yeah, so fantastic results. I mean, especially about past accretion history of the Milky Way. I won't ask you any scientific question though. I'm just very envious that your satellite has already launched and it's worked so well. And I'm just, for people in the room who are working on Euclid, what didn't work out, and do you have any advice for us?
What didn't work?
In Gaia, you get the impression that everything worked perfectly?
Wow.
It didn't.
No. No, I mean, especially, well, for me, I'm working on the RVS, and when the satellite was launched on the first months, it was saying, oh, there's this stray light problem. Everybody was saying, this is going to be unuseful. And I was there saying, I'm going to do the chemical abundances. People were almost laughing. So, because, yeah, I mean, there were lots of problems. And indeed, I really have to, I'm amazed by the work that has been done on the RVS by the people, many of them here at Meudon, working on the RVS spectral extraction, and they have been not only capable of tackling this problem of the stray light, but also modeling, as I said before, this systematics with time. Oh, it's true that they have data every day, everywhere, all the sky. So, and they have been able of doing this and offering us wonderful, wonderful data. But yeah, sure. And also, well, it's important also to keep all. Yeah, and keeping people motivation through years. I mean, I've been working on Gaia for 18 years. It's easy to say I arrived here as a postdoc to do this job. So I can almost say my postdoc has finished this year. So wow, it's crazy. I've done it. Okay, I've been recruited at CNAP for doing this job, and I was here several years ago motivating my recruitment. I hope that today I have shown that my promises are today a reality. So yes, I think this also for young people. I was discussing with the PhD students before, just believe in what you're doing. We are doing crazy things, but this is why science is beautiful, right?
So you have 18 more years. Okay, any other questions? No, so let's thank. Sorry? Okay. So thank you very much, Alexandra.
Thanks to you, really. Thank you.